Hi, Assalamualaikum warahmatullahi wabarakatuh, my dear students. Madam Ruby here again, logging in for lesson 57, Isomerism of Organic Compounds. We need to define what is isomerism and stereoisomerism. What are structural isomerism, chain, position, and functional group isomerism? What is geometric isomerism and optical isomerism? We need to explain geometrical isomerism due to restricted rotation of the carbon-carbon double bond and single bond in cyclic compounds, and identifying cis-trans isomerism for a given structural formula. We need to be able to define chirality center and enantiomers. And then what is optical activity by drawing a pair of enantiomer using 3D formula. Next, we need to be able to state the applications of chiral compounds in daily life. Isomerism can be divided into two parts, structural or constitutional isomerism or stereoisomerism. Both of these is divided into different categories. Category 1 is chain, and then positional, and then functional group for structural. Whereas for stereoisomer, it is whether geometrical or cis-trans or optical enantiomer. What is isomerism? It's the existence of different compounds with the same molecular formula but different structural formula. The atoms are arranged differently. Different structural formula that have the same molecular formula are called isomers. Two types of isomerism are structural isomers or constitutional isomers, or isomers with the same molecular formula but differ in the order of attachment of atoms. And B, stereoisomers, or isomers with the same molecular formula but different arrangement of atoms in space. Structural isomerism or isomerism that results from different order of attachment of atoms. There are three types: chain or skeletal, positional, and functional group isomerism. For chain isomerism, the isomers differ in the carbon skeletal, meaning it has different chain. It can be linear or branches, and it possesses the same functional group and belong to the same homologous series. That's the characteristics of chain isomer. For example, 4.7 question number 1, let's draw two isomers for the molecular formula C4H10. The first one is a linear, or the name is butane, and the second one is a branch compound, and the name is 2-methylpropane. For positional isomerism, the isomers will have a substituent or a functional group in different position. For example, question number 2, we are going to use the molecular formula C3H7Cl. So let's put the Cl on the first carbon, and then the name would be 1-chloropropane. But if we put the chlorine at the second carbon, it's going to be 2-chloropropane. So both of this compound is isomers to each other. Other example of positional isomerism is 1-butene and 2-butene. This is not listed in your course book, but you can write this down in your exercise book. And this is C8H10 for 1,2-dimethylbenzene, 1,3-dimethylbenzene, and 1,4-dimethylbenzene. All these three compounds are isomer to each other in terms of positional isomerism. Another example given to you is formula C6H13N consists of a cyclopentane with two substituents, amino and methyl. Here, amino would be the parent. Therefore, the carbon that has amino would be the first carbon. Another isomer would be methyl group at carbon number 3 of the cyclopentane. The methyl group is at carbon number 2 for the third compound, and the methyl group or the carbon is inside amino itself. Now let's look at an alcohol here, C4H10NO. 1-butanol is also called N-butanol because N is for normal, a linear compound. And then 2-butanol is having the hydroxy compound at carbon number 2. And also we can rearrange the methyl group so that one methyl is attached to carbon number 2. So the third compound is named 2-methylpropanol. The third structural isomerism is functional group isomerism. The isomers in this type of isomerism have a different functional group, and they belong to different homologous series having the same molecular formula. Different classes of compounds that exhibit functional group isomerism are shown in table 4.2, but they are in pairs. If you have an alcohol, the functional group isomerism would be ether. If it's aldehyde, the partner is ketone. Carboxylic acid is with ester, and alkene would have a partnership with cycloalkene. Example 4.7, question number 3. We're going to do C2H6O. So the first structure is ethanol. The partner would be ether, so O would be in the middle. Dimethyl ether is an ether with 2 carbons. The second example is C3H6O. It can form propanon, whereby the carbonyl group is in the middle here, and it can also form propanal, whereby the carbonyl group is on the first carbon. Another example is C3H6O2, propanoic acid. The partner is an ester, whereby the carboalkoxy group is shown to you here, C double bond O, O, and the name for this ester is methyl ethanoate. Okay, let's do question number 1A of practice 4.4, C5H10. So we need to make sure that the number of carbon are 5, hydrogen are 10. So the formula that we are going to do is CnH2n, which is most probably an alkene. So CH3, CH2, CH2, okay, there is one double bond over here, and then this is the end of it. There would be one more H over here. okay, for this carbon. So this is basically 1, 2, 3, 4, 5. This is pentene. Pentene. Okay, we don't need to put pent 1 in or 1 pentene if the double bond is at carbon number 1. Okay, what is the chain isomerism for pentene? Okay, let's make a branch over here perhaps. Okay, so CH3, CH2, and then this is where we want to put a branch, and then we have the double bond still over here. Okay, so this would be named as, this is carbon number 2, so 2-methyl butene, 2-methyl butene. So this is a chain isomer for pentene. All right. Another type of isomer is positional isomerism. So we need to move the position of the double bond. So it would be, maybe we can put it in the middle somewhere. So CH3, CH, and the double bond would be here. CH, CH2, CH3. So this would be 1, 2, 3, 4, 5. This is carbon number 2. So pent 2-ene or 2-pentene. Okay, this is a positional isomerism. Positional isomer. Okay, you can do a branching. Put this one here, and it would be another chain isomer for pen-2-ene. Okay, what about the third one? Functional group isomerism. So for functional group, functional group, you can make a cyclic compound. Can we do a cyclic compound? Yeah, a cyclic compound that has 5 bonds. So let's count 1, 2, 3, 4, 5 carbon, and each of the carbon would have 2 hydrogens, so it would be an alkane. So this is the functional group isomerism for this molecular formula, and the name is cyclopentane. Okay, that's it. Let's do question number 2. There are 7 structural isomers of C4H10O. Draw a pair of skeletal, positional, and functional group for the isomers. So firstly, we write the long chain or the linear chain of butanol, CH2OH. There are 4 carbons. Hydrogen, we have 10, and this is 1 O. So butanol, the skeletal or the chain isomerism would be CH3, CH2, and then maybe we would like to put the CH2 over here, and then the functional group is here, and another H should be here lah. So this is the 1-methyl propanol. Okay, so carbon number 1 is here, the one that is attached to the hydroxyl group, the parent. Okay, this is a chain, and now we are going to make a positional. means we need to switch OH into a different place. This is carbon number 1. So CH3, CH2, maybe we're going to put it at carbon number 2. See, this is OH here. So CH and CH3. So this is called 2-butanol. 2-butanol because the hydroxy compound is at carbon number 2. Okay, the last one is functional group isomerism. Functional group isomerism is when you have a different functional group. So the pair for alcohol would be ether. So we draw an ether where we put O in the middle. So this is diethyl ether. Next, we do question number 3 for the formula C6H9Cl. Draw a representative pair of isomers illustrating each of the following types of isomerism. So for chain, we are going to do a linear first, CH3, CH2, 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 Cl, and then we're going to do the one that has branches. Okay, so we put a branch here. Okay, and this is the chain isomerism, where we have a substituent methyl from the carbon number 2. And then we do a positional. Positional means we must switch the position of the substituent or the parent. So now the positional would be CH3, CH2, maybe we can put the Cl here. Okay, so just CH and CH2, CH3. So the position of the Cl now is at carbon number 2, whereas the first one here we put at carbon number 1. Carbon number 1, this is carbon number 2. Okay, so there you go, the answer for question number 3, practice 4.4. Okay, now let's look at the second part of isomerism, which is stereoisomerism. It arises from the different arrangement of atoms or group in space. So it involves 3D arrangement. The two categories for stereo is cis-trans or geometric isomerism and optical isomerism, or the thing that involves with enantiomer. Cis-trans isomerism results from rigidity in molecules. It occurs only in two classes of compounds, alkanes because it has double bond, and cyclic compounds due to the rigidity of the ring. There are two requirements for geometric isomerism to occur. The first one is there should be a restricted rotation about a carbon-carbon double bond and alkenes, or a carbon-carbon single bond in cyclic compounds. The second requirement is each carbon atom of a site of restricted rotation must have two different groups attached to it. Cis isomer has the same atoms on the same side, whereas trans isomer has the same atom on the opposite side. Let's look at example 4.8, number 1, on 2-butene. As you can see, the restricted carbon is carbon number 1 and carbon number 2. And then each of the carbon has a different group attached to it. The left and the right carbon has CH3 and H, a different group attached to the restricted carbon, and when it is on the same side, it is a cis, and if it is on a different side, methyl here, hydrogen here, it is a trans. For the second question, let's look at a cyclic compound whereby the restricted carbon is a single bond of a ring. So the compound is cyclohexane, and as you can see, the restricted carbon on the left and the right has a different group attached to it, H and CH3 respectively. So when it is on the same side, it's a cis. When it's positioned on a different side of the restricted carbon, it is a trans. For example, 3 and 4, we show to you here the restricted carbon has the same group attached to it, or here in 1-butene it's the same hydrogen atom, so there would be no cis-trans isomer. As also this second compound, 1,1-dimethyl cyclopropane, it has the same 2-methyl group at the carbon. The restricted carbon is here in the cyclopropane. So if one of the doubly bonded carbons has 2 identical groups, geometric isomerism is not possible. Since cis-trans isomers have the same functional group, they have the same chemical properties, but because of the length difference, they would have a different physical properties. For example, melting point of trans isomer is higher than cis isomer, and then boiling point for cis is higher than trans. This is due to a difference in polarity, because cis are polar but trans are not. This is what I meant. For cis-2-butene, you can see that the compound is slightly round. It is shorter, so it has higher density, 0.6 to 1, and it has higher boiling point. More energy is needed to break the intermolecular forces among the molecules, since they have a compact structure. But for trans-butene, it is as if the compound is linear, as you can see here. So the density would be 0.604 because the surface area has expanded greatly. Therefore, the boiling point is lower, 0.9 degrees Celsius. The second stereoisomerism is optical isomerism. Optically active compound, when it has a chiral carbon in the middle, it can rotate. If it goes to the right, we call it dextrorotary, D. If it's go to the left, it is a levorotary, L. So the angle can actually be measured by using polarimeter. This is the mechanism where polarimeter is used. So what are the requirements to be having optical isomerism? The first one is it has to have chiral carbon or chirality center. We also call it stereogenic center, whereby the carbon here is a sp3, an sp3 hybridized carbon atom, because it has 4 different groups attached to it, P, Q, R, and S, so we call it a chiral carbon. And also B, the second requirement is molecule is not superimposable. You cannot superimpose it with its mirror image. So we have to look at the mirror image after this to prove that it is not superimposed. Now, this is the star that we put at carbon to label that it is a chiral center, and here all the groups or atom that attach to carbon must not be the same. Well, basically, stereoisomer has two types. Number one is enantiomer and number two is diastereomer. But we're going to focus on only enantiomer. It's a pair of mirror image molecules that are not superimposable. It's a pair of enantiomer that have identical chemical and physical properties, but differ in the direction of a rotation of a plane polarized light. Meaning that if we draw them and then we draw also the mirror image, it's not going to become superimposed, and then it would have a direction of L and D, dextro and levorotary, as we have mentioned earlier. This is an example of an enantiomer whereby the molecule selected is 2-butanol. The carbon in the middle here is labeled as a star, and R and S is also stands for the dextro rotary and levorotary. Okay, and you can see here, this is the condensed structure, and then the chiral carbon is here, and then attached to the chiral carbon is the hydrogen, this one, and then the hydroxide group, this one, the methyl group is this one, and the ethyl group is this one. So we can see here that all four groups that attach to the carbon is not the same. And then we draw a mirror image, a mirror here, and get the mirror image over here, whereby now the hydrogen is on the left and the methyl is on the right. So for enantiomer, you must draw it three-dimensionally. That's a must. Here is another example of 4.9, question number 2, 2-hydroxypropanoic acid. You can see in the middle there, this is the chiral carbon. Attached to it is a hydrogen, hydroxyl group, methyl, and carboxyl. If you draw a mirror there, you can also draw the mirror image whereby now the hydrogen is on the left and the methyl is on the right. Now, what is diastereomer? Let's just read some notes about it. It's a molecule containing more than one chiral center. Diastereomer are not mirror image to each other. All physical properties are usually different. This is two examples of application for chiral compound in our lives. In the hospital, they use negative dopa for the use of treatment for Parkinson's disease, but positive dopa cannot be used because it's toxic. And then S-ibuprofen is the popular analgesic, whereby the active ingredient is Motrin, Advil, and many others. Okay, practice 4.5. You have to determine whether these compounds can exist as a pair of cis-trans isomers or not. If the cis-trans exists, draw each of the cis-trans. So you need to be able to find the requirements, the two requirements for cis-trans to exist. Having the restricted carbon, whether it is double bond or single bond in cyclic compound, and also for each of the carbon that is restricted, it must have a different compound. That's a requirement. And for practice 4.6, you need to draw the pair of enantiomer for 2-bromobutane and 2-chloropentane. I believe this should be done easily. That's all for lesson 57. I hope you would do the practices on your own first before looking at the answers that we are going to provide soon in the Telegram channel, inshallah. With that, I leave you until next time. Assalamualaikum warahmatullahi wabarakatuh. Bye.